Okay, so moving on. So I'm just going to talk about the stability of phases very briefly. And then I will probably end this lecture because I think I'm liking the shorter lectures. Maybe you're liking the shorter lectures as well. So let's just briefly talk about the stability of phases, and then I'll cut it off. So we recognize here, let me draw a phase diagram really quick, okay? So I'm just kind of drawing a fictitious one, so something like that. P versus T, and maybe this is my solid area, my liquid area, and my gas area, okay? So now what this diagram is showing you right here is if we were to start with a liquid and cool it down, so in other words, if let's say I started somewhere here and at the same pressure just decreased my temperature. Well, look, for a same given pressure, I would move that way. Let's make that a different color. Okay, so I would move along this line right here. This is what I would observe. Okay, this red line corresponds to this red line right here. And so what I would see is as I was decreasing the temperature, I would see that liquid cooling down. And as I crossed this point right here, okay, that point is represented by this entire area. And so if I was keeping track of the time, how long it took for my material to cool down, there would be a lag in that time as it is transitioning phases, okay? And that is due to the latent heat of the phase change. Or in other words, the enthalpy of this case, the enthalpy of fusion is what's driving that constant temperature. And what's also important to note, I can never get this liquid colder than its freezing point. Now, of course, there's caveats to that. Many of you, I know, are aware of what's called supercooling. And so if we were to observe supercooling, we would actually see like a tiny region where the temperature of the liquid drops and then rebounds, okay? And so there's usually a specific set of conditions that you have to observe supercooling, okay? And I'm not gonna go into that in too great a detail right now. But if we were doing this nice and steady, if we didn't have, well, actually what we would need is a nucleus. So one way you can get supercooling is if you don't have a nucleation point. So oftentimes electrolyte solutions will have supercooling because they have little particles, little ions in there that can serve as seed crystals. So I guess I did just describe supercooling, random professorial side tangents. In any event, for most pure phases, you will not observe supercooling, and you'll see this lag due to the enthalpy of fusion. Okay. So what I also want to talk about in this now, because I'm talking about time, is thermo versus kinetics. And as an example, the standard chemical potential, so that means at 298 of graphite, is actually less than the standard chemical potential of diamond. So let's think about what this means. So at room temperature and pressure, the chemical potential of a diamond is actually greater than the chemical potential of a piece of graphite. So it actually should be spontaneously undergoing a phase transition, right? So if you've got a diamond, I don't have a diamond. My wife doesn't have a diamond. Say what you will. But if you had a diamond, it technically should be going under a phase transition right before your very eyes into a piece of graphite. But why doesn't this happen? Well, because the kinetics of that phase transition, the rate constant of that phase transition is crazy slow. It's got a half-life that's like the age of the universe, okay? So that phase transition happens much faster when there's more pressure and more temperature around. So even though the phase diagram might suggest that, oh, this phase shouldn't even exist right now, in certain materials, oftentimes kinetics can win. Kinetics can actually beat out the thermodynamics, okay? And so we have to be careful when we're talking about kinetics and thermo, okay? Because they often are not connected to each other, and thermo might predict one thing, but kinetics says, yeah, that's true, but it's just going to take a hell of a long time for it to happen, okay? And so let's see. With that, I'm going to end this video. That was nice and short and sweet, and then we'll pick up with the next one. Okay, folks. Hasta luego.